talking about visually and numerically describing data. Um, and we're going to use it in some applied settings. So for instance, this individual was talking about the impacts of COVID-19 on race, and it says data is the only way that we can see the virus. We have only indicators. We can't actually look at a person and tell who's been infected. So what we have is data right now. Okay. And this data that I have was obtained from the CDC. And they say the data is still incomplete, but most of the data on deaths is 90% complete. Okay. They also make a statement that saying communities of color are being hit disproportionately by COVID-19. So using this data, does the graph or the data support these statements? And this section is in part on visualizing data. So does the graph support this claim? I'm going to start off by discussing what's called a bar graph. Now, a bar graph lists on one axis the category, which in this instance is going to be the race or ethnicity. And on the y-axis, or not always the y-axis, in this case the x-axis, we're going to list the percentage or the count. If you have the percentage, it's the same as knowing the count, and vice versa, so long as you know the total number of people that are involved. Now, the percentage is obtained from the count by taking the count for that category and dividing by the total number of individuals. Okay. So let's look at this graph and see if it supports this claim, because it's a little bit easier than looking at the table, and that's why it's so visually appealing. Keep in mind that in order to construct a bar graph, you have to have this table that's listed here with either the category and either the percentage or the count. Okay, so here's the graph, and this is from the CDC. This is COVID deaths by race. And what it shows is that the highest proportion hit with 57% is white non-Hispanic, with 57% accounting for the death. The next highest are black non-Hispanic, accounting for 18.4%, and then Hispanic Latino with 14.8%. So this graph doesn't support the claim made by the individual saying that the hardest hit was minorities, but this graph can be misleading. What this graph fails to take into account is the proportion with which these individuals occur in the population. So for example, and I'm just making this up, if blacks or Hispanics account for 2% of the population, extremely small, okay, but they're being hit with 14% of the deaths, that's disproportionate with respect to their prevalence in the population. And that's what this graph fails to reflect upon. And if you take that into account, those statements are correct. They're just not reflected in this graph. So you have to be careful with your statistics that you don't have confounding or lurking variables in your data. And you have to carefully explain why you're using those variables to represent them. Okay? So to answer the question, yes, whites do account for the majority of the deaths, but it doesn't account for the proportion of the population. Okay? Now, I want to go back to our main discussion, which is visualizing bar graphs. And so I'm going to briefly discuss how to make one. Then we're going to go through an example of how to do that. Okay. So a bar graph is for a qualitative or categorical data. Okay. And it lists the category or demographic on one axis and the frequency on the other. When we list the counts, the bar graph is called a frequency bar graph. And when it lists the probability or proportion, it's called a relative frequency. So it doesn't matter if we use frequency or counts, they're fine. And relative frequency, which is an estimation of probability, is the number of occurrences divided by the total number of observations, the sum of all frequencies. Okay. When you're given raw data, you must arrange your data into a table, as we saw before, and then you can put the table into a graph. So let's go through a quick example of this. So here is some demographic information. Okay. And this is how the data will occur to you in raw form. You'll just see the categories that occur, and you have to count how many males and females there are and put them into a category. So our categories are the different outcomes of this category. It's male versus female, and this is typical of most places of employment. Okay. Then on one axis, you might have a count or a frequency, and we just count how many males there are. We see that there are 8 and that there are 10 females. And if I want the relative frequency, I just take the count and I divide by the total number, which is 18. Okay, so now I can make this into a graph. And this is what it looks like with the counts. So we have category on x-axis and count on y-axis. It doesn't matter which axis you put it on. So as you can see, this one has the category on the y-axis and the count on the x-axis. So long as there's a category and there's a count or a relative frequency on the other, you have a bar graph. Okay. So that's all there is to making a bar graph. Now I talked about how the different types of variables, discrete, continuous, or categorical and categorical, will affect your analysis. So a histogram is used for a quantitative variable. And here's an example of it. So this is an article that appeared on the New York Times, and it's linked in right here if you want to explore more about it. And we will see more of this later. And what it lists is the summer temperatures and from 1951 to 1980. And then in this graph to the right, you can see that old graph from 1951 to 1980, then the new graph, the new histogram from 2005 to 2015. And it doesn't have a number on the x-axis, which it should, but it's decided to categorize it. And this, it shows that there's a normal range here. There's a most common outcome, and that peak occurs in this middle. That is actually the average temperature, is that peak, okay? And this describes a normal distribution, okay? You can see that there's some colder periods and there's some warmer periods, but most of them fall, the average falls right in the middle there. And you can see that as the time goes on, from 2005 to 2015, this histogram has shifted. The average value has moved to the right, indicating that temperatures have gotten warmer over time, okay? And that the average, which occurs at the peak, roughly in this range, is now in this hot category, and sometimes reaching the extremely hot being much more likely than in this graph from 1951 to 1980. And that there is a wider range of outcomes that occur, a wider range of temperature ranges. So we need to discuss how to make a histogram, more about normal distribution or normal graph, which these both describe, and how to interpret this graph. So here's a little bit more information about these graphs. Okay. So these are all involved, these graphs are all histograms, and the frequency or probability is listed on the y-axis and the temperature on the x-axis. You could also list the counts on the y-axis, but that's less likely. And the graphs compare the temperature over time and showed that there's a general increase in temperature as we saw, and that the average, which is that peak, has shifted from normal to a hotter range. And histograms are extremely useful to compare two populations. So in this case, we're comparing a pre and a post. Okay. Okay, so we can see that there's a little bit more variability in the data. The range has increased. And one note on that is that global warming is kind of a poor name for what we're experiencing, which is the climate change. It's not that things are always getting hotter, it's that there's more extremes on either end. So either really hot or really cold. So the range has increased. Now, one of the most important things that we'll come back to is that these histograms reflect what's called a normal distribution. And the peak is in the middle, the general shape is a bell, and it's symmetric about that middle. Okay, so if you were to fold it in half about the highest peak, it should be roughly symmetrical. Okay, and in that middle, that represents the average of a normal distribution. Now, here's a quote from Dr. Hansen. It says the data really highlights that changes in the average, while they may seem modest, have big implications for extremes, and that's what's going to affect society and ecosystems. Dr. Sanford said, the findings reveal what has happened so far, also provide a glimpse into what's in our future. Okay. Now, for each time period, the distribution of the summer temperature forms what is known as a bell curve or a normal distributions, because the most common outcome was the average, okay, occurring near the peak and forming the bump or a bell in the middle. More extreme temperatures, which happen less frequently, fall in the ends, okay, with heat waves on the right and cold snaps on the left, okay. Um, so Dr. Hansen talked more about the variability, um, and there are other scientists so for example, this Zeki, who's an energy systems analyst at UC Berkeley, have pointed out that this effect is mainly a reflection that some parts of the world are warming faster than others. So that's what the increased variation or range is doing. Okay, so I talked extensively about normal distributions that you might see on a histogram. Here are some other shapes of distributions that you might see. So the one that we talked about is this normal distribution. It has one mode, one most common outcome. It's right in the middle. Then we have skewed distributions, which you'll see quite often, actually. So keep in mind, nothing's ever perfectly normal, has this perfect symmetry. So a lot of times I'll ask you, is it approximately normal? Remember, when you're working with data, nothing turns out exactly on the dot to be like exactly, to have exactly the shape or exactly that number, but does it represent it? Okay, then there's these skewed distributions, these two, and a uniform distribution here. And here's a bimodal distribution. There are two modes. Bimodal distribution sometimes means that there's two different populations out there. Okay. And there's two forms of bimodal. There's symmetric and there's this non-symmetric. The non-symmetric is kind of more common. Okay. Here, this has a narrow range. It's more narrow than this normal distribution, but it has a similar one. Here's has a little bit more spread. This is probably more similar to what you might see. If you were to see something that resembled this, you might say it's approximately normal. This one, you would be hesitant to say that it's approximately normal, and you can see it has an outlier. Now, outliers don't mean it's not normal. Normal distributions can have outliers. Keep that in mind. Okay. Now let's look at some more histograms. Okay. So these are the coronavirus infections as of 12/5/20 from the CDC. And this is a histogram, and you can see it is bimodal. Young kids don't seem to be really getting the coronavirus that are under 17, but from 18 to 29, there's a peak. Okay. Then it kind of goes down, then it goes back up from 50 to 64, and then it starts going down. Okay. Now, this indicates it's bimodal. If we look at this distribution, two different populations right here. Okay, and the two populations would be younger versus older populations. And in order to construct this histogram, I'm going to go over the histogram and then talk about what the histogram represents in a little bit. When you look at this histogram, what you really have is you have a similar table to a bar graph. You're going to have to divide up your data by the years. So we have 0 to 4 years. That's we're constructing a category out of numerical data. We have 5 to 17 years, and etc. 18 to 29, 30 to 39, 40 to 49. Okay. And the key thing here is that no one is counted in an age group twice. Okay. Then we can have the count, and then from the count we can form the percentage. You can list the count or the percentage on the histogram. One that lists the percentage is called a relative frequency histogram. It's also estimating the probabilities of an outcome. Okay, I personally prefer the percentage, but it makes no difference. Okay, so in order to construct a histogram, we're going to need to make a table just like this. I'll walk you through the steps, but let's talk about this histogram and what people are saying about it. Okay, so it says the histogram for infections of COVID show a bimodal distribution. We've already talked about two different populations. The younger group and the older group are the two most common outcomes. And experts have cautioned that the seemingly new prevalence among young people may be in part a reflection of more widely available testing. Okay. But the growing numbers of people hospitalized in states like North Carolina, Texas, also suggest increased transmission of the virus. Even now, people younger than 50 are being hospitalized at a far lower rate than people older than that. Okay. And while the effect of the coronavirus on younger people may not be highly associated with hospitalizations and death, they do act as a transmission connector for individuals that could in fact be at higher risk. Okay, so we're seeing a bimodal distribution in part because there are two different populations and attitudes towards risk, and that the increase in the youth could act as a transmission and connector to older generations. Okay, and so one could be fueling the other. Okay. Now we can see the impact of coronavirus by death versus age group also obtained by the CDC, and here's its histogram. We can see that the risk for younger individuals is much lower than it is for individuals over 50. So here's 50 to 64, and it goes up a lot more. So even though the infections are far fewer for this age group, 70 to 84, 85 and older, we can see that far more are dying from it. So it's disproportionate to the number of infections. And when we're talking about disparities between the graph in the beginning, with the coronavirus deaths by ethnicity, this is the same case. So the deaths by age group are not proportionate to the number of infections. Okay, and I just want to reiterate that this graph is formed from a table, and so you first need to construct this table. It has the age group, and then the percentage or the count, and then you can form that table that we just looked at. So I've been talking about building a histogram and that you need to build this table. Here's how you'd build a table, okay? So, and by the way, when you're talking about a histogram, one of the important features is its shape of the distribution, okay? So that you can make conclusions about it. And that histograms should be used for quantitative random variables. So to construct a histogram, you need to find the range, and the range is the maximum observation, the largest observation minus the minimum. Then you need to form your categories, which is often referred to as bins. So right here, these are your categories, age group. That's also called a bin, okay? So your bin, you need to decide how many of them you want on n. And I said typically n is 5. That's kind of a lie. It can be larger than 5, so keep that in mind. It can be as large as 10, but typically people prefer around 5 or 6. And if you're doing it by hand, you should typically always use n equals 5 because doing it by hand is very painful. And most of the time you're going to use a computer. Okay, but I might have you do it once or twice by hand so that you know what it's like. Okay. And so now you need to construct the class width, which is nothing more than the width divided by, which is nothing more than the range divided by the number of bins, and that's your width, okay? Then you have to construct your K classes or bins, and this is how you do it. You start with the minimum plus K times your width, and K is going to range from 0 to 5, okay? And your first class is going to go from your minimum plus K times the width to the minimum plus K plus 1 times the width. And it's open on the left and closed on the right, except for your last interval, okay? And when K is equal to N, you have this class, okay? So now let's construct this these classes and form our table. Okay, so here's some example data. So here's data, as you might observe it, is just data. So our largest observation, our largest observation is not 11, no, it's a typo. It's 12, so I needed to fix that. But here's the data that as you would observe it, our largest is 12. It appears right here. And you subtract it from the smallest, which is negative 13. Okay, so you subtract it so it's a double negative. We have a range of 25. I've decided to take n equals to 5 classes. Okay, and then I'm going to form the width of each bin, and that's going to be 25 divided by 5, which is equal to 5. And then we form our table. So I have my class or category. It starts at the smallest observation minus 13. Then I add my width to it. So my width is 5. So I go from minus 13 to minus 5. That has a length of 5 between those two numbers. Then I pick up at minus 8 and I go from 8 and I add 5 to it. That's negative 3. Then I pick up at negative 3 and I add 5 to it. I go to 2, etc. Okay. So now I formed my frequency by counting how many observations lie between 13 and minus 8. So I go to this data, how many observations lie between minus 13 and minus 8, but I don't count minus 8 because of this interval. Does not include minus 8, and I see there's 1. And I go through this, so how many Observations are there from -8 to -3. So I go through it, -8, there's 1, 2, 3, 4, 5. I don't count -3 because I don't include the endpoint. So I have, again, 1, 2, 3, 4, 5 observations, and there it is. And I keep going through this, okay? And this is my frequency count. So now I can form the histogram, and this is what it looks like. Here's an example histogram, okay? Now, this histogram looks like a normal distribution. It has that general bell shape. So I want to talk more about this normal distribution. It's also symmetric about the middle. It has a most common outcome. Its average lies somewhere between -3 and that should be +2, so I apologize. And if we look at this, here's a bunch of different normal distributions, and I want to form talk about how these different distributions are different. Okay, so this dark blue one here, it has a mean of 0, and we can see that occurs right about where the peak is, right there. So we can estimate the means. This red one does too. So the means are this Greek letter mu that occur right here. And so these three that lie right here all have a mean of 0. This this green one has a mean that occurs at -2, so we can trace that back and we can visually see like what the average value is. Okay, and going back to these normal distributions that have a mean of 0, we can see that this one right here, this dark blue one, it has the smallest standard deviation or standard error. That's the sigma squared. That's called the variance. It has the smallest one, so it has the tallest peak. It says with much more certainty, most of the observations lie between -1 and 1, but for the red curve, that occurs less frequently. So the standard deviation says that the average occurs much more often or much less often. And so the standard deviation is highly related to probability and really important in statistics. So these sigma squareds, these variances, as they start increasing, this red one starts to flatten out. There's more spread, and then this green one has a variance of 5. It really flattens out and decreases that peak. So there's more variability and more spread in the data. And we can see that's what was happening with that temperature one. It got more spread out, its peak flattened, right? And its peak shifted. Okay, so here's our normal distribution. And please note, it's really important to know which histograms are more variable and where is the average. So those are two key points, is mean and variance and recognizing a distribution. It's symmetric because if I fold it about this mean of 0, I get exactly the right-hand side and the left-hand side, okay? Okay, so you're never going to see those perfect curves. You're going to see a curve that's generally like this, and I have a normal distribution or bell-shaped curve superimposed on the histogram. In real life, you're going to see a histogram like this, and you might see ones that are slightly more skewed, and you have to determine if they're normally distributed. So if you saw this histogram, I hope that you would agree that's approximately normal. Okay. Now, I talked about the averages, so here the average is 0, and its variance, well, we need to determine how to calculate that. So for normal distributions, they have their peak at the mean, and the population mean is the same as the sample mean. Most of the time, you're only going to be able to calculate this, the sample mean, because you won't have access to the data for the entire population. And to calculate a sample mean, all you do is you add up all your observations and you divide by n, the number of data points. And these two formulas for population versus sample are the same. That is not going to be the same for variance. Okay, so variance, that sigma squared, is going to say, take your observation, subtract your mean, and square it. Okay, and this is what it would look like. This is variance. And if you have a sample variance, that is, your data is a subset of the population, you do not divide by n, but you divide by n minus 1, and that's very important to remember. Okay, so remember, sample variance is you take your observation, you subtract your sample mean, you square it, then you do the same for x2, you take x2, you subtract the sample mean, you square it, and you repeat that for all your observations, and you divide by n minus 1. Okay, s squared is called the sample variance and should be used when you have a sample of the population, and sigma squared is only used if you have the entire population. Okay, now the units of population variance and sample variance are squared units. So oftentimes we'll take the square root, and that's called standard deviation. Okay, so sample standard deviation and population standard deviation are going to have the same units that you originally started with, and they often make more sense. Okay, so that's all that we have for today on describing data, okay, after you've collected it. And these will be your first steps in data analysis. Thank you.